you guys have a good spring break? Alright, so we are gonna need to take off the water hat and put the dynamics hat back. So, but I have two announcements for you. Next week on Tuesday, we are gonna have a visit for the Wall of Wind. So the director of the Wall of Wind asking me that all of you need to wear not sandals or flip-flops. You need to have a closed-toe shoes. And if you have a hard hat, bring it with you, because they only have 50 or maybe less. So we are having 60. I'm not sure that maybe not all of you are gonna come. So just to make sure that you have a hard hat on you. So this is the first announcement. On Thursday, we're having our second midterm. The second midterm is gonna include, I believe, 2 questions on the fluid dynamics and 2 questions on the parts before fluid dynamics. Do you guys remember we had work and energy and we had impulse and momentum? So absolutely, there may be a question on work and energy and a question on impulse and momentum, and 2 questions. I don't know actually what you guys have in fluid dynamics, so I'm gonna take the questions from Professor Leon and include it with my question. The parts that are gonna be covered this week is not gonna be included in the midterm. Maybe, I don't know, like maybe a question or something, but it depends on how much time the other questions are gonna take, because I'm gonna ask Dr. Leon, maybe it needs 30 minutes, we'll see. Okay, so that's the 2 announcements for now. So what I'm gonna do today is, you guys remember 1 month ago, 3 weeks ago, what did we take? Does anyone of you remember the last lecture that we had together? It was structured dynamics, right? Okay, that's good that you guys remember it's structured dynamics. So let's see what we have here. Okay. So what we are studying since the beginning of the semester is mechanics. So we need to understand how bodies move. But when we design structures, we don't need our structure to move. Okay? So we need our structure to stay still. Okay, that's what is the purpose. However, when we put loads on our structure, they have to move. For example, and there is what we call is structure analysis, regular structure analysis, and why we do structure analysis. You guys remember why we do structure analysis? Like if we have, for example, a bridge like this. Maybe it's an arched bridge, something like this. Why we do structure analysis for this bridge? Why? Just imagine why the science of structure analysis is needed. Okay? For 2 things. We need to know the forces inside our structures. I need to know when you put load on this girder or in this slab, what is the bending moment on this slab is going to be. Okay? Because if this slab cannot take bending moment, it's going to fail. So we need to design this slab for bending moment. And how much shear force this slab is going to have. So I want to know what is the shear force in this slab, or it's going to fail. And I want to know what is tension or compression on this slab. So we need to know forces inside the structural members. Because this is very, very important information. This is the general information that any structural engineer needs to know. Why we do structure analysis is the basis for any structural engineer. You need to understand structure analysis very well so that you can be a structural engineer. Looking at any structure, bridges, buildings, you need to understand how this building is holding itself. Okay? So I need to know what forces inside these members, and to know these forces, I need to do structure analysis. I need to know what is the axial force in this column. What is the bending moment, like this one, how it's gonna bend? What is the shear force here, like how they're? What is the normal force in these cables? What is the force in this cable, in this arch, or in this cable? I need to know all the forces. Once we know the forces inside the members, once I know how much tension force here, I can design this to resist this normal force. Like for example, if I have a normal force of 10 ton and I apply 10 ton normal force in this bend, it's gonna tear, right? Because this bend is not designed to take 1 ton force, but if I go 1 kilogram, it's gonna take it. So I need to know the forces applied on my member so I can design the member to take these forces. For example, if I have this column has 100-ton load, and I want to design this cross section, I can make it big, I can make it small, I can put reinforcement in it, I can put lots of reinforcement. So when we design columns for buildings, we need to know what is the cross section and how much reinforcement in this cross section. Okay, so that's how can I understand, or how can I know that? By knowing the forces on this member. So the first thing that we do structure analysis for is to get what is called number 1, internal forces. Okay. Number 2 is to get deformation. All right. Internal forces, we use it for what is called strength-based design. Strength-based design. Deformation, we do performance-based design. Okay, strength-based design, so I need my members or my structure members to have the strength that can resist the force with. So I need to know what is the forces here. So next year, did any of you start any structure analysis classes? So I believe you start to do analysis for like trusses, for beams, for frames. So that's what the structure analysis do. And all what you do in this course is to get internal forces, get reaction, get the bending moment, get the shear force diagram. That's what all the structure analysis courses do. Like I teach next semester an advanced structure analysis course, and also all what we do is to get internal forces. Either regular one or advanced one. We get reactions, we get shear, we get normal, we get bending, we get all the forces. We don't do design. We just get what forces inside each member of the structure, okay? What about the deformation? Why do I need deformation? So, okay, strength-based design, your structure is designed to take the forces and everything's good and it's not gonna fail. But this is not the only concern. The concern is, my structure can make this and it's not gonna fail, but it's not comfortable. Like if I'm putting table, I can't have the table like moving around. If I'm living in the 60th story in a tall building, I can take like my building doing this. It's not gonna fail, but I can't, it's uncomfortable. So I need to know the deformation that my slab or my beam is gonna have, so that I can put limitation on this deformation. So it's not only about strength, it's also about what we call serviceability or comfortability. Okay, so you need to be comfortable. So that's what we do performance-based design. We need it to perform very, very good. That's why we do structural analysis. How about structural dynamics? Structure dynamics. So structure dynamics is a special branch of structure analysis that covers the behavior of structures subjected to dynamic loads. Okay, so all our loads right now, as I said before, it's a static or what we call dead or live load. This is still a static load. Like this is a static, doesn't move. So load concentrated at a specific area doesn't move. Also, you guys give me example of dead loads that can be on a structure. Dead, that means that doesn't move. Furniture. This. However, some people, okay, actually I might do a renovation and I change the chairs of place, or I have a table at home and I change the place. It's still a static or dead load. Why? Because we don't care about the location of your furniture. What we do, we calculate all the loads of the furniture, and actually we melt it down on the whole floor and say, okay, the live load in this floor is 200 kilograms per meter square. Unless if you have a very, very heavy load concentrated at a specific area. Like let's say that you have a swimming pool at a specific area that's very, very heavy. So that's why we need to consider this load especially. Or you have a very, very heavy lightning fixture or something. Okay, so that needs to be considered especially. Okay, so all our loads are still what we call static loads, dead or live loads, either dead or live loads. What are the dynamics loads? You guys give me example. Well, people moving is not that big dynamic load, but if it's a car moving on a bridge, that's not a static load. It's like truck load or something, and it has its own way when we do analysis. Okay, so I'm talking about real dynamic loads, big loads.
How about the wires in the bridge?
What do you mean the water on the bridge?
Like an bridge, like a hanging bridge. And because
Like rainwater, or you mean like a bridge that holds water in it? There's some actually I saw bridges that has water and has boats on it. So that's but I'm talking about the main dynamic loads that can impact structure, and there's two of them: wind load and earthquake loads. So was one of them? Okay. So wind loads is a huge dynamic load, and earthquake is a huge dynamic load. That's why we need to learn this branch of science so that we can solve these loads, structural dynamics. And if you guys remember from last time, I started to do a few things. I drew like a building this way, like a multi-story building, something like this. And we said to do dynamic analysis for such a structure is very, very complicated. It has many, many degrees of freedom. We have to do simplification to this structure so that we can solve it. Because this has, I'm not sure, maybe hundreds or thousands of degrees of freedom. What I mean by degrees of freedom, each one of these nodes can move differently, okay? So once you have lots of degrees of freedom, that means that you need to find out what is the deformation at this point. Like this point can move this way, can move this way, can make rotation. Same thing with this point, with this point, with this point. But we need to do some assumptions that are reasonable and allow us to solve this structure easily. How? Knowing that, for example, this slab, this floor that we are sitting on, can this point move differently from the point here if an earthquake hit? Because it's a very, very rigid slab. When a slab hit, we all are gonna move this way, right? Like not like a chair is gonna move the other way. So, or I mean a fixed point on this slab. So all the points are gonna move this way. So if we assume that all the points on this slab is moving together either X or either Y or rotate, so is that assumption valid? Mm-hmm. It's valid, right? Unless this slab is not rigid, it's flexible. And when this slab is flexible, when you have lots of voids in this slab, like you have a void for the stair, a void for the elevator, it is not rigid anymore. It might make, like this or like this. What I mean by rigid means like it can move this way, okay? So I can assume that all of these points on this slab are gonna move this way. And if you guys remember from last time, we said that if this column and this column and this column, all these columns have the same delta, is that a barrel system or a series system of stiffnesses? Do you guys remember we talked about barrel? Okay, so we did something like this. I did like, if I have a column like this, or a bar and another bar, and they are fixed here, I can represent this bar by a system of stiffnesses like this has K1 and K2, okay? This column or this bar, like two bars like this, okay? Fix it here, and I'm applying tension this way.
Thank you.
If I'm applying tension this way, what is the force in this part? If this force is B, what is the force here and the force here? Both of them has B, because the B transferred to both of them. But if this one very, very stiff, it's gonna have a little deformation. But if this one is like rubber, it's gonna have a very, very long deformation. So they can have different deformation, but they have the same force, the same applicable force. So if I put B on them like this, so this one is gonna have B and this one is gonna have B. But this one is gonna make delta, like delta 1, and this one can make bigger delta, delta 2. And the final delta on the structure, delta equal delta 1 plus delta 2. Okay? So that's what we call series stiffnesses. On the other side, if you have the wall here, and you have the first stiffness like this, and the second stiffness like this, and they are connected to a rigid body, and you apply a force this way. This rigid body is gonna move this way as a one clock. It's gonna get here. So both bars have the same delta. Like this bar is gonna get here, delta 1, and this bar is gonna get here, delta 2. So delta equal delta 1 equal delta 2. However, this one is gonna have B1 and this one is gonna have B2, depends on the stiffness. Okay? So the bigger the stiffness, the more force is gonna absorb. Okay? Alright. So here you have B equal P1 equal P2, but delta equal delta 1 plus delta 2. All right, so let's apply this concept here in this building. If you push this slab and it's gonna go this way, this one is gonna have delta, 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 all of them are gonna move together, right? Like let's assume this slab is attached by a column in these four quarters and it's moving this way. All of them is gonna have the same delta in the x direction.
Yeah.
So is these the stiffnesses of these columns are series or barrel? Like if this one has K, K, K. Let's focus. You are gonna look at them, oh, they are going this way, they are all series, okay? But it's not like this, let's look this way. All of them has the same delta, so they are better, like they are all have the same delta, delta 1 plus delta 2, so they are all in in barrel, okay? So if you wanna get the sum of the stiffnesses of all these columns, you just sum the stiffness, like the total K of them is the sum of Ki from I1 to I equal to n, which is K1 plus K2 plus K3 up to Kn. You just absolute summation of all these stiffnesses, okay? Same thing for this story. You sum all the stiffnesses in all these stories. So once I reduce, or what we call do reduction of the system, is gonna be something like this. Like a one column, and here's the mass number 1, mass number 2, 3, 4, 5, 6, 8. So this has the sum of all the stiffness, K equivalent of the story number 1, K equivalent of story number 2, 3, and 4. Right? Why? Because all these has the same delta. Alright, so this is for one story. What if, when an earthquake hit this building, actually the delta is going to be something like this. Yeah, each story are having the same delta. So this is delta 1, 2, 3, 4, 5, 6, 7. Each story has the same delta, so all the columns at the same story are in barrel. But how about if we want to lump sum all these deltas? Look at this. If you want to get the delta of all the structure, this delta, they are summed up together. Like here's delta 1, and actually this is delta 2. But this is delta 1, and this part, so they are getting summed together. Same thing what happened here. You have a small delta and a big delta, but the final delta is all delta 1 plus delta 2. So when you calculate the stiffnesses for multiple stories together, they are in series. So the same story are in barrel, but the multiple stories are in series. So because this is going to be something when they oscillate, it's going to be something like this. They add up together. So if I want to sum the stiffness K1, K2 up to Kn, you guys remember what the rule that we have here to sum all these stiffnesses? If you remember from last time, that the K equivalent of systems in series is equal to the multiplication K1 multiplied by K2 multiplied by K3 up to Kn over the sum of Ki from I equal to 1 to I equal to n. I proved it last time. If you want to go back and check, I have it still in the notes. You can find out how we get the K equivalent of this system. So that means is that I can reduce this multi-degree of freedom system. Look, this is a multi-degree freedom system, but it's very, very complicated. I reduced it to another multi-degree freedom system, but it's less complicated. What I'm doing right now, I'm gonna reduce it to a single degree of freedom, one mass, one stiffness, K equivalent, and M equivalent. So what is this? These are equivalent systems of my structure. They are gonna behave the same like this structure. If you apply an earthquake to these three systems, this earthquake has this. If you apply this earthquake to this, and that, they all are gonna have the same delta. So this one is gonna have delta, delta, and delta. They all have the same delta. Okay? So what we do is just we are simplifying our problem so that we can solve it. We can solve this manually. Like we can do it with manual, and I'm gonna solve this one actually in a few minutes. And you are gonna see how much time this one is gonna take, maybe 40 minutes, to solve just this system. So can you imagine a multi-degree freedom system, how much it's gonna take? So if this 1, 2, 3, 4, 5, 6, 7, so this is gonna be a matrix, 7 by 7. You need to solve 7 by 7, 7 equations. It's very, very hard, okay? This one is impossible to do it, okay? So usually when we do like even computer software, if I give this structure to a software, and to be honest, in my advanced structure analysis, we tried to solve 60-story building, and I forgot in the ETAPS model to say that this slab is rigid, or we call it diaphragm. I forgot to say that, so that I can tell the structure, try to reduce this system to this system and solve. It takes days, and it didn't even solve. Like the model is like taking until the next week, and it didn't even solve. I didn't know that. Like I didn't know that I didn't activate that, and then I found out that I didn't say or didn't tell the software, consider these slabs are rigid so that you can condense this system from this 1,000,000-degree freedom system to just a 60-story that has 60 degrees of freedom. Okay? And when I did that, it took like 3-4 hours, and it solved, and we got resolved. Okay? So can you imagine this? This is gonna be way, way more simple. Okay? So that's how we condense the structures. However, there's something else other than the stiffness that we can consider when we solving structures. And I told you about this last time, that we can consider what is called the damping force. Like if this is the mass of your structure. When I say mass, it's usually the mass of the slab. Because the slab system or the floor system of a structure is considered like 90% of the mass of the structure. The other masses, like the columns, they are like 10%. So when we say mass, usually it's the flooring system of the whole structure. We consider the stiffnesses of the column because the stiffnesses of the column is one of the most important elements in resisting the lateral load, like seismic and wind load. Also, there is a force called the damping force. Do you guys remember the damping force? We call the we put this. Let's make this something a little bit fancy, like putting the spring. It's something like this. Because when you have a structure, this spring is like, which is the column. And actually this spring is the shear stiffness of the column and the bending stiffness of the column. Because if you have a structure, it's moving this way. So there's a shear on the columns and there's bending on the columns. So that's how is the spring working. And we put this symbol for damping. It's like, do you guys know the hydraulic arm? The hydraulic arm is something like this. This is how we, and here's you have an oil. So this is what damping is. Sometimes we put in our structure, there is like real damping, like it happens when you have an earthquake hitting a structure, the joints start to open and close. Like the columns start to have cracks, and this cracks dissipate some earthquake energy. And sometimes we add real dampers. We add hydraulics. I'm not sure if you guys see it before. Like in some structure, we put like a truss element from here, this point to this point, and it has a hydraulic arm. So when an earthquake hits, it dissipates some energy, keep going in and out. Also, if you have a swimming pool, a water tank on top of your building, all these are considered as dampers in your system. It dissipates the energy of the earthquake. Like an earthquake hit this way, the water tank goes the other way. So this is our different ways of dissipating energy. So this is our system, our mechanical system that we need to solve. So let's use the Newton's second law to solve this system. You have a mass, you have a stiffness, you have a damping. So to solve this system and make it more visual for you, this is the mass of your structure, M, and this mass is connected to a spring that has a stiffness K, and connected to a hydraulic arm that has a damping C. And there is an earthquake is hitting on this structure with a force that is vary over time. So this is Ft. So there's a force F. It changed over the time. Okay? We need to solve this system. Let's assume that our mass under this force is moving this way. This is the direction of the movement. And it's gonna move with an acceleration ma. So this is ma. And based on Newton's second law, you guys remember some Fx? The summation of the forces in the x direction, and this is the positive direction, is gonna be equal to m ax, right? What are the forces in the x direction? We have how many forces? Okay, let me tell you. This is a force, and this spring has a force. You guys remember the force in the spring? No, this is energy. When you say square, it's gonna be energy. So the force in the spring is K multiplied by delta. The force in the spring by the delta in the spring. The hydraulic arms, the forces in them is C multiplied by U dot. The delta is U. Delta is the displacement. We can say delta or we can say U. So the K stiffness multiplied by displacement, and the other side, the C, which we say the coefficient of damping, is in proportional to the velocity of the structure. Like we say K is proportional with U. Okay? So this is C multiplied by U dot, and this is actually the force inside. I'm not gonna say where it's coming from, but this is the force in this arm. Let's put all this in this equation. All the forces in the x direction, I have this force, and this force. The positive force is Ft is positive. We have Ku is negative Ku, and I have Cu dot is negative. All this is equal to m multiplied by a. And a is a U dot, U double dot, right? U double dot. So let's manipulate this equation. It's gonna be m, let's make it bigger. We're gonna have m U double dot plus Cu dot plus Ku equal to Ft. So what I did, I said all this on the other side and kept the equation. This is one of the most important equation in the structure analysis field, this equation. Okay? We call this equation the structure, the equation of motion. Equation of motion of structure. Right? This is very, very important equation. Okay, so there's two elements of this equation, left-hand side and right-hand side. The left-hand side, we call it the forcing function. No, sorry, the resisting function. Resisting function. And the right-hand side we call the forcing function. Why is that? Okay, so we have a structure, force applying on this structure wanted to damage it. So this is a forcing, can be an earthquake, can be wind, can be whatever hydraulic arm is pushing on your structure. So this is the forcing function. What is resisting this force? This force has to overcome three components: the mass of the structure, the damping potential of the structure, and the stiffness of the structure. The more stiffness that you have, so you are gonna resist this force. The more C, the more damping, you are gonna resist this force. So we need to solve this equation. And what I mean by solving this equation? Finding what? Finding M, finding C, finding K, finding F, U, whatever. So, solving this structure, do you guys remember if we go back here to solve the structure, we need to find internal forces and we need to find deformation. But actually deformation is the way that we can find forces. So we need to find deformation. Deformation here is what? Is U. We need to find delta. U is the same as delta. Once we find delta, the whole thing is done. Okay? So what I mean by find delta, I can see U here, I can see U dot here, U double dot. This is not a regular equation. What we call this equation? If there's dot or U double dot. Math, 2 years ago, if you have an equation that has derivatives. What this equation is called, differential equation. Do you guys remember there's different types of differential equation? This equation, second order, but we call it very linear. Why it's linear? Because none of the derivatives are squared. All of them are to the power 1. Linear, second order. Why it's the second order? Exactly, because the highest derivative is differentiated 2 times, so it's second order. If this is differentiated 3 times, it's gonna be third order. And we call it also second order non-homogeneous equation. Why it's non-homogeneous?
Because it's not equal to 0.
Because it's not equal to 0. If this is equal to 0, it's gonna be homogeneous equation. So if we were able to solve this structure, this equation, and get you, we are done. We identified how the behavior of this structure is gonna look like. And let's find out if we will be able to do this in the next 40 minutes to solve this equation. It's gonna be a long run. Okay, so we're gonna do a little bit of a heavy math here. So I need all, the last time I studied math was like 10 years ago, 2008, 2009, so it was like, oh yeah, a little bit, like 15 years ago. Yeah. It's the damping coefficient of the structure. Coefficient. We usually assume for a structure have 5% damping, but when we add more dampers, you have more capabilities. This is gonna change. It's gonna be a special structure. Okay.
Professor, what is it that you drew the arrow at the end? U is equal to what?
U?
Yes.
This one? This one? So this is the displacement. That's what we need to find out. If we were able to find U, U is the delta. Like if you have a structure is pushing this way, I want to find the delta up there. How much delta this structure is going to have.
But I understand that, but you're.
It's a check mark.
Oh, it's a check mark?
Yeah.
Oh.
Oh, this one I'm saying like once we find it,
Oh.
all things
Oh, I
going to
thought.
Yeah, me too.
Let's
Yeah.
put question
I
mark.
thought it was a
So
B.
you were right.
Because we didn't solve it yet. All right, so what I'm gonna do today is, I'm not gonna solve this equation because this is very, very hard. What I'm gonna do, I'm gonna neglect the damping. Okay, I'm gonna neglect because this is gonna take hours if it has damping. And I'm gonna make the force F is equal to 0. So it's only have mass and stiffness, okay? But if you want more knowledge, I have some notes from the earthquake engineering that has solving the equation with damping, solving the equation with a harmonic force, solving the equation with a seismic force. It has everything. But what we are going to do in this class is that solving what is called single degree of freedom system. Right. We are going to solve a system that is number 1 on damped single degree of freedom system under free vibration. Okay, so undamped single degree of freedom system on a free vibration, it is the same problem that we have over there, but we only have a mass, and this mass is connected to the stiffness. Okay, and there is no force here. The equation of this system is like this: is M U double dot plus KU is equal to 0. We call this free vibration. There is no force that can cause vibration, so it's a free without any force. Okay. All right. How can we solve this system? So let's find out. All right. This is a special equation from the other equation. Let me ask you: is this still linear? Okay. Is it still second order? Yes. Is it still non-homogeneous?
No.
It's homogeneous, right? Because this is 0. So this equation is linear second order homogeneous differential equation. Alright, let's solve this one. So I'm gonna make this equation u double dot plus, I'm gonna divide over the mass, k over m, u is equal to 0. You guys remember how we solved this equation? No idea, huh? Okay, so we solved this equation by assuming the answer. Doesn't make sense, huh? But we are not gonna assume the whole answer. We know the physics of the solution. Like we anticipate that a structure either has, when you apply an earthquake on a structure, it's either the motion is growing up or either the motion is decreasing down. Like it's gonna be damped until it becomes to 0. So it's a Gross equation. Okay? So when we say Gross equation, it's exponential. Either the exponential to the power positive. The positive means that the motion is increasing. Negative that the motion is decreasing. So if you guys remember solving differential equation, we always assume the answer. So the solution, we say that assume that u, which is the answer, is equal to a constant v multiplied to e, which is exponential to the power rt over time, because it's function in time. It's either the motion is growing over time or decreasing over time. So r might be positive, might be negative. So what we need to find out, what is v and what is r? Once we find them, so we found the answer. Okay, if u is equal to b exponential e to the power rt, what is the value of u dot? B is constant, r is constant, t is variable. Er, e to the power rt, right? What is the u double dot? Dr squared e to the power rt. So I found these two. Let's substitute with u and u double dot in this equation. So when you substitute, it's gonna be dr squared e to the power rt multiplied, sorry, it's u double dot right away. And then you have k over m multiplied by u, which is b e to the power rt. All of them are equal to 0. Okay, so we can divide by this. This is going to be gone. This is going to be gone. So we will be left out with that r squared So r squared is equal to negative k over m, right? Because we drive, okay, so when we have u and we get u dot, we get the derivative with respect to the time. U dot is the time derivative. So when you, this is the variable that you get the derivative with, so it stays the same. We just take the constant out. Like we are saying, like if we're saying e to the power 5x, get d dx to y. Like this is y is equal. So when we take, it's going to be 5e to the power 5x, because we get the derivative with respect to the variable x. Okay. All right. So we have r squared is equal to negative k over n. What is the value of r? I'm trying to be very, very precise. How can I get r? That's a basic math.
Square root of
I'm going to take a square root, right? So it's going to be the square root of negative k over n. What is the square root of this? Imaginary, right? Because there is negative under the root. So if I want to take the negative out, so I have to put I out. So it's going to be I, but when you take the root, this can be plus or minus, right? So this is going to be plus or minus the root of k, root plus or minus I, the root of k over m. And actually, this quantity, root k over m, this is, you should know it. This is called omega, the angular velocity of the structure. The stiffness, the square root of the stiffness over the mass. This is something from A6. Okay, so I can remove this and I can put plus or minus I omega. This is what R is equal to. Okay, so this is something that is proven. You can go and search online where this is coming from. And actually omega is also equal to 2 pi over t. Like if you have a circle and you want to find the angular velocity is the circumference of the circle, how much time you take to do all this round. So this round is 2 pi over r, 2 by r, and you have you did it in a time t, so you did 2 pi over time t, so this is the omega. Alright, so omega has two expressions, and I have everything in the notes, okay? Alright, just root k over n, that's what we need now. It's equal to omega, and I found it here, so I remove it, and I put omega. And we have I out here, so we have R is equal plus or minus I omega. So I can actually say that U is equal to, I can substitute back in U. Substitute in U. So U is equal to e to the power R, which is plus or minus I omega, and I have E. Okay, so I got this one. And since you have two roots, plus or minus, we can separate these two into two solutions. Like we are saying that U has a bar V1 e to the power I omega t, and has a bar V2 e to the power negative I omega t. You can have a bar that is growing and a bar that is decreasing. So this is our equation. Okay. Right, so the last thing that we did, that we said that U has a bar that is growing, V1 e to the power I omega t, plus V2 e to the power negative I omega t. Right now we need to link, there's a formula is called Euler's formula. I believe that you guys take all that in math, you just need to go and revise. For Euler's formula, if you want to connect real numbers with imaginary numbers, I, real, and this is the number 1, and this is the imaginary number I. So, any point that has imaginary and real numbers can be described this way. Like, if you have this circle and this angle is phi, so the e to the power I phi is equal to cosine phi plus I sine phi. If the angle phi is 0, like it's equal to 0, like here, so cosine phi is going to be equal to 1, and sine phi is going to be equal to 0, so the number is real, 1. But phi is if it's 90 degrees, so cosine 90 degrees is 0, and sine 90 degrees is going to be 1, and the number is going to be I. So for Euler's formula, that's actually the formula. E to the power I phi, which is in general, is equal to cosine phi plus I sine phi. You can search it also online and find what is the root for Euler's formula. We'll find lots of information. E to the power negative I phi is equal to cosine phi minus I sine phi. Okay, so let's use Euler's formula here and see what we're going to get. So we have I to the power to positive power and e to the positive power and e to the negative power. And phi is corresponding to omega t, because I have I and I have omega t here. So we can remove phi and put omega t and substitute in this equation. So if we substitute with these two here, what we are going to get, U is going to be equal to P1 multiplied by cosine I omega t plus I sine shouldn't have I. This is just the omega t. Because the I is outside, so phi is just the omega t. This one. So this is gonna be omega t, and the I is outside, and then you have here sine omega t, plus B2 cosine omega t minus I sine omega t. So this is how I used the Euler's formula in the equation of the U. I know it's a little bit of a heavy math, but we're gonna do it. Okay, so I have here cosine omega t and cosine omega t. Let's take cosine omega t as a common factor. So U is gonna be equal to cosine omega t multiplied by v1 plus v2. And then you will have sine omega t plus I sine I think we can take I and A and sine as a common factor. So you are gonna so here you are gonna have sine omega t, and you will have b1 plus b2. So b1 and b2 are constants, so we are gonna put them as a one constant. Like we are gonna say that b1 and b2 are gonna be equal to a1. So you will have to sine omega t. Same thing. This is not positive. This is negative because you have here b is multiplied by negative and b1 is positive with respect to the sign. So we're gonna put negative here. So this is not positive. So since this is b1 minus b2, so this is gonna be plus a2 sine omega t. And I wanna say that all the omegas that I wrote here, they are called omega n. And n represent natural frequency. Natural frequency, that means there is free vibration. Because if you put a force, omega can be omega d if you have damping. Yeah.
For sine omega t, where does the I go? Because it goes from like there, there's like an I in front of it, and
The I is gonna be here as well. Like you can put it here. I mean like you can put it, we can put it I here and I here.
do we have to, or
I think, yeah. And it can goes inside the constant A2.
yeah, it's part of it.
Yeah. So the only, okay, so cosine omega t can be taken as a common factor. Like if I break this down, it's gonna be b1 cosine omega t, b1 I sine omega t, b2 cosine omega t minus b2 I. So I can take cosine omega 2 as a common factor and sine omega 2 as a common omega t as a common factor and put all of them in one thing, and then all this is gonna be a2 and all this is gonna be a1. And all of them start to be as a function in sine and cosine. And that's actually what the exponential function can be extended to sine and cosine. So once we have them this way, we can get u dot. For u dot, I can differentiate this. What is the derivative of this? It's negative sine. Okay, but what is the whole thing? So it's gonna be negative a1. But there's something before I write the sign. There's omega t.
Oh yeah.
So I have to take the omega out. So I have sine omega t. This one plus a2 omega cosine omega t. Right? So we can actually put some boundary conditions here and say, what if at t equals 0, the structure can have u, and u is equal to u naught, and can have u dot, and u dot is equal to u dot naught. When the structure start the motion, can have an initial displacement and initial velocity. So let's find out what is the values of u and u dot at t is equal to 0. All right, so if we put u at t equal to 0. And we call this boundary condition. Boundary condition, that's something that we know some information about. So let's put t equal to 0 here. Cosine 0 is going to be equal to, sorry, this one, this equation, a1. So this is going to be a1 multiplied by, when t is equal to 0, what is the value of the cosine?
0.
Cosine 1. How about a2? It's going to be 0, right? So this is going to be equal to a1. So a1 is equal to the displacement at t equal to 0, which is u node. So this is very, very important. a1 is equal to u node. How about u dot at t equals 0? This equation, if t is equal to 0, it's going to be negative a1 omega multiplied by 0, because this is sine. And then you will have plus a2 omega cosine 0, which is 1. So this is equal to u dot node. So this one is going to be 0, like this one. And you will end up with that a2 multiplied by omega is equal to u dot node. So a2 is equal to u dot node over omega. So we were able to find out what is the value of a1 and what is the value of a2. Check one thing very quick. Yeah, I think we're good. Yeah. All right. So let me write. Let me continue over there. Okay, so let's continue this. So can you guys tell me, after we know what is the value of a1 and what is the value of a2, what is u is equal to? This is the general equation of u as a function in a1 and a2. Right now we know the values of a1 and a2. Can we substitute them in the main equation?
Yes.
So how it's going to be? U is going to be equal to u naught, right? Multiplied by cosine omega plus u dot naught over omega sine omega t. We are very close, okay? We still didn't fully solve the equation. This is also very important. Okay, we need to do something, a little bit of a math tweak. We are going to divide by something that is going to make this problem very, very easy. If we are assuming, or for example, we are saying that this angle is phi, okay, general angle, and this is u dot node over omega, and this is u node. So this is going to be u node square plus u dot node over omega all squared. Just want to make sure that I have the triangle right. Yep, that's right. So I have this here and this here, okay? Assuming this. So what I'm gonna do, how about if I divide all this equation by this? Let's see what is the magic is gonna happen. If I divide this equation, this over u node squared plus u dot node over omega all squared is gonna be equal to u node over the root cosine omega t plus u dot node over omega all divided by this root, and then you have here sine omega t. This root is this root and this root. I divide all the equation by this value, okay? Alright, what is this is gonna be? U node over this. What is gonna be? When you divide, look, this is phi. You have, this is the opposite, u node, and you are gonna divide it by this line. How's it gonna be? It's gonna be sine phi, right? And when you divide this over this, is gonna be cosine phi. So this equation is gonna be equal to u over this root is gonna be equal to sine phi plus multiplied by cosine omega t plus this is gonna be cosine phi multiplied by sine omega t, right? Is that okay? All right. Do you guys remember when you have sine cosine plus cosine sine? Did you hear this rhythm before?
Yeah.
Sine cosine plus cosine sine.
Yeah.
What is this equal to? Okay, this is equal to sine of the summation of these two angles, sine of omega t plus t. When you have, I believe it's in the equation note, there's, I believe some, or in the sheets that I give to you, if you have sine cosine plus cosine sine, so it's gonna be equal to sine omega t plus cosine t, and there is a way that this can be cosine the two angles. And there's something, I believe, if you guys remember, sine 2 theta is equal to sine theta cosine theta. I'm not sure if you guys remember that, so there's lots of geometric equations. Alright, so right now I have u under this root is equal to this equation, so I can say that u is equal to this root, which is u node squared plus u dot node over omega all squared. I'm gonna multiply this here, multiplied by sine omega t plus t. This is the solution of the equation that was here like an hour ago. Okay? So this is so fun, huh? I can imagine this is the easiest one. If you look at the other ones, they are horrible. Okay, so here's u, and this is the solution of the equation. But let's actually understand what is this solution. Okay? This solution has two parts. Has this part and this part. But let me ask you something. What is the maximum value that you can be? The maximum value happen when the maximum value of the sine is happen, which is 1, right? So if the sine is 1, this one, the u is going to be equal to u naught squared plus u dot naught over the omega all squared. So we call this the amplitude, or the maximum value or amplitude. And we call this the magnitude. Alright? Let's draw this actually, how it's look like. So if we are trying, because this is function in t, u is function in t, and all this is kind of like sub-variables, omega, phi, and don't forget, phi is function in u node and u dot node, okay? Alright, so let's see how this look like. If we are trying to capture the displacement of the structure u over time, and we are gonna try to draw a general function, it's gonna be maybe something like this. So if the structure starts at displacement equal to 0 and velocity equal to 0, this line is gonna be here. But I draw it to be general. Why? Because I assume that this structure has u node, and this, which is the slope of u, which is the u dot node. That's what I assumed for the structure. But if u dot node is equal to 0 and u is equal to 0, it's going to start from here. So let's put the maximum amplitude, this, we call it the maximum. This distance is equal to the root of u node squared plus u dot node squared over omega. This is the maximum that can happen. And what is this? You guys tell me, what is this time? The time that the structures need to do one cycle. Like it goes u this way and come back to its original position. We call it
Frequency?
not frequency, it's called the periodic time. The periodic time is the time that requires the structure to do one cycle around itself. Like this structure is going to move this way, coming at displacement delta, and go back to 0 and do negative delta and come back to 0. So this is how it happens. So we call this t. What is the relation with this with frequency? It has a relationship. T, the periodic time Tn is equal to 2 pi over omega n. And actually that's what we wrote here. If you look here, you will find omega n is equal. So what I did is a swap. Look here, omega is 2 pi over t. This is the angular velocity. So if I want to find t, t is going to be 2 pi over omega. All right, so, and we can actually imagine this as a circle, like if the structure is gonna move, because this is part of a circle, like if this is gonna be something like this. And let's say that it starts from 0 and it keeps moving. This is the u that it's making. So this is u. This is u maximum. Okay? And this is u here is equal to 0. This is time. So u here is equal to 0. And the structures keep moving on this circle until it comes here. And then it goes down. And then it goes in the negative. And then come back to the original position. That's what happened here. Like here. And it goes to the maximum u. And then goes down. And then goes to the negative and goes here. So if you divide this into quarters and put them together, it's like a circle. Okay? Like if you bring this part down here, so that's what happened here. So this, let's say that the structure started here from this point. So this is gonna be u node. And this part is gonna be u dot node, like this part, over omega. And this is phi, and this is the u maximum. And when it gets here, where is the maximum u? U maximum. Alright? So, is that difficult? It's really difficult. Yeah, well, this is how actually if you're gonna solve it manually. And guess what? Sometimes we solve this with multi-degree freedom. You don't only, where's the verse equation actually? Here. This mass cannot be a single number, it can be a matrix. Because if you have a multi-degree freedom system, you are going to have a matrix of masses, a matrix of stiffnesses, and you have to develop a program or a code, do some coding to solve this equation, getting something that's called the eigenvalues. It's going to be more and more complicated. But guess what? If you understand this very, very good, you're going to be a really good structure engineer. This is how to be because nobody was tall building designer or somebody who do design for a high-rise building don't know this concept. You cannot be a structural engineer without knowing the concept of structural dynamics. You need to know how everything here is getting solved at. If you are just sitting on a software putting some numbers, this is not going to work. You will not be able to judge these numbers. You need to understand how is everything here is working. Okay? So I'm just saying that you need to understand a little bit in depth. Okay, I'm just gonna show you the results. So this is if it's without damping. I'm not gonna solve the other system, but I'm gonna show you how does it look like if the system has damping. Alright, if the system has damping, look, I'm not gonna ask you like a heavy question in this. I'm gonna ask you about the concept. For example, how the single degree of freedom response look like with like single degree of freedom, undamped single degree of freedom system. Maybe you need to write to me this curve. This is how it's gonna look. Maybe this is how does the equation look like. If it's a damped, it's gonna be something like this. So the structure is gonna have still sinusoidal wave, but what happened in this sinusoidal wave? It's damping, it's dying out. Why? Because there is something that makes this force doesn't vibrate forever. And that's actually how the real application is. Like if an earthquake hitting a structure, the structure is not gonna move forever, right? It's gonna damp until it dies, until the displacement becomes zero. Like this one is gonna be very, very small like this, okay? So this is how the final response. U is equal, like let me put the equation so that you can imagine. It's a little bit bigger equation, so U is also equal to a square root, a different one. E is to the power negative. And then you have omega nt, and here what's called damping coefficient. When the damping is bigger and it's a negative, what negative means that is it growing or is it dying? It's dying, right? So there's a damping and there's negative, and also you have sine omega d t plus t. So it's the same thing. You have a square root, which is the amplitude, the maximum displacement, and then you have an e, which means that it's a factor that makes your sinusoidal waves die out. So you have e to the power negative xc omega nt, and xc is called the damping coefficient. Damping coefficient. So in an exam, if I give you a shape like this and I ask you, is that a damped or undamped system? It's damped system. But if I give you system like this one that doesn't die out, so this is undamped single degree freedom system, like the one that we solved it. Okay? Alright. But this is a still, we can call it free vibration. Why free vibration? There is no forces applying. But if a force applying, so this is gonna have two components. This component and another component from the force. Like let's say that the force is an earthquake. The earthquake is something like this. It's gonna be added to this. Or there's a force that is sinusoidal wave. It's gonna be something like this. F with time. So this is gonna be added. So it's gonna be have this part and this part. Okay? So that's why I want you to understand how does the different system look like, how to build the equation of the motion of the structure. So I might ask you how to build the initial equation, the one that I wrote, like mu double dot plus cu dot plus ku is equal to 0. I might ask you the equation of each system. So you need to understand this stuff. Okay, in the last 5 minutes, this one? Well, this one is a free vibration. Okay, it's called damped. That's the difference. Damped, single degree freedom system, under free vibration. When we add vibration, like loads, this is going to be added on top of it. So it's going to have different shape. When you add something like this to this, it might not damp and damp a little bit, and maybe something like this. Depends on the type of the force. So we need to add both of them. Let me tell you application very quick in 5 minutes. Why this is important. What we do actually in seismic engineering using this concept. Okay, let's assume that we have an area like Miami, and Miami has lots of tall buildings, something like this. And maybe some, maybe a high-rise building, something like this, maybe single-family homes, two-story multi-family homes, and small buildings like this. Our Miami got exposed to an earthquake. This earthquake is something like this. The earthquake is one earthquake that has one graph. Has like age of the earthquake, something like this. The responses of these structures are different. Like, for example, this structure is going to respond this way. It's going to be, for example, once we solve it using the 1 hour equations that we have been solving, the response of this structure is going to be, for example, U, once we solve it, is going to be something and that has a B, something like this. This structure, once we get hit with an earthquake, T, is going to have different response because it's different structure. It's going to be something like this. This structure, completely different response. T with U. And this one is going to have different response. T, something like this. You tell me why each structure has different response.
The weight,
The weight, the mass, what else?
the height.
The mass, the stiffness, the damping. Each structure has different masses, completely different. So they definitely have different responses. So what we do in seismic engineering, we get thousands of virtual and real buildings and apply an earthquake to them and capture their responses. And we only care about the maximum response because that's what's going to make the maximum displacement. So let's say that it's going to have U1. Let's say that this is going to have U2. This is going to have maximum response U3. And this is U4. And we get the maximum response either positive or negative. It doesn't matter. So this is the maximum responses. each structure has its own fingerprint, and the fingerprint that we call the structure with, it's the periodic time, the natural periodic time of the structure, T. T1 of this structure is equal to root, we got T actually, like we said T is equal to 2 pi over omega, and omega is equal to root k over m, so this is going to be 2 pi root m over k. So P is special for each structure because each structure has a mass and stiffness. Okay? So this structure has different mass and different stiffness. It's going to have T1. This is going to have T2, T3, T4. And this is the most important component about the structure, the periodic time or the natural period of the structure. T. Why it's natural? Because it doesn't depend on the force. It's just a number that represents the mass and the stiffness. That tells me, is this structure flexible? If the, like two buildings in Miami, like 60-story ones, they have a natural period maybe in 10 seconds. Like this building, take 10 seconds to goes this way and come back to its original position. But if it's a 2-story building, it's gonna be fast. Because it's small. It doesn't like make all this. So this one is gonna have low natural period. This one has a big natural period, maybe 10 seconds. Actually, there's a formula that says that the T of the structure is equal to, I'm not sure, like 1 second if it's 10-story, like 0.1 multiplied by the number of the stories. So if it's a 10-story, it's gonna be 1 second. If it's 100-story, it's gonna be 10 seconds. But this is an empirical one. But how I can get this? I make a model on a structure software. The software calculate the mass, calculate the stiffness, and gets you all the period of this. And we drew a curve. And this curve is function in the time and the acceleration or the displacement of the structure, U double dot. The structure, not the earthquake. The acceleration by the earthquake has one single acceleration. But each structure is going to have different displacement, different velocity, different acceleration. So, and in this plot, for one single earthquake, we plot T1 with U1, T2 with U2, T3 with U3, like XY coordinate system. It's going to be something like this when you plot these points. Okay? So it's going to make a curve like this. What is this curve? We plot U1 with T1 as a one coordinate system, XY. And this is as an XY, 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 and put all these points here. This is not 8 or 10, I'm talking about thousands of points. Do some statistics and come out with this curve. So this curve represents of what? We call this curve, this is very, very important term. Response spectrum curve, which means the response of a spectrum of buildings, okay, to one single earthquake. But we can rely on one single earthquake. We have a suite of earthquake that we applied on a structure, like there's one El Centro that happened in California, Luma Creek, like there's lots of earthquakes, and we put all of them, something like this, and then. So each earthquake, we apply on the structure, we get a curve. And finally, we get the mean and standard deviation. So the mean of these curves is something like this, and something like this, and we call this the response spectrum that we use to design buildings. So when it comes to seismic design of building, the concept of response spectrum, this concept is very, very important. To be a designer of a building, you need to be familiar with this one. I tried to condense a whole course, actually 2 courses, dynamics of structure and seismic engineering in just one lecture, trying to give you a high level idea. But if you want to go very in depth, when you get in graduate school, you might pick a structural dynamic class so that you can have basics to study seismic engineering and do these stuff. Okay? Once you have full grasp on these 2 classes, I believe you are ready to understand how tall buildings are performed. Okay? All right. So we are done with the dynamics part. Next time we are gonna start with the rigid body motion. Okay? See you guys next time.